Hello, Mr. Wilson. Mr. Wilson. Mr. Wilson. Hello, Mr. Wilson.
Yeah, Joshua, what are you saying?
Please, there are a lot of people in the lobby. Can I admit them?
Yeah, go ahead, admit. Today, you admit. The other be able to me admitting on.
Sharp. Hello, Mr. Wilson.
Yeah, Joshua.
I beg, you believe if you take this advertisement, say.
You see that thing?
Mm-hmm.
Yeah.
Hello? Yeah, good evening. Sorry, but you're fine. Are you busy? Listen. Yes.
Yo, Mona.
Have you started?
Yeah, we are starting now, and we are trying to get people to join, but we are just going to go ahead and start.
Okay.
But you still have this your DP or profile picture, whatever. Okay, good evening, everyone. Welcome to another session of the makeup class. Initially, we had planned, I know we had said that, yeah, sorry, I know we had said that we are going to do the assignments and discuss around that today. And so from above. We are going to discuss the details of the assignment tomorrow, but today will be more like a guide to help you develop the right ideas about some of the concepts in the assignments. And then tomorrow we'll proceed with the details of the assignments, and then it will make everything far easier to understand. So please bear with me. Don't worry, tomorrow we will tackle the session. Even if not tomorrow, we will be sure to do it before it is too late. Okay. If you have any question, do not hesitate to raise your hand and then ask. Right. I will start off by explaining concepts concerning the Little Man computer, then the CPU operating system simulator. And also I will try to hint around regions that are crucial to the assignment. So listen closely as the lesson progresses. Remember to ask questions, raise your hand if you have any queries. As for media, if I start, I go at full speed. So if you don't interrupt at a point, mean you will die, I tell you. All right. So the Little Man computer. when we began our very early sessions, this was the first thing we looked at, and I explained to you that it's basically an interface that tries to mimic how a central processing unit works. And to an IT personnel or an IT student, it's very crucial. It helps you understand the build or the architecture of the central processing unit of a computer. This one brings it to a more humanly understandable form. That is why it's basically showing you things that do not exist in real life. So this is not an actual computer. It's basically something that is meant to look like what a real computer should be able to do, or the central processing unit of a computer should be able to do. This is a Higginson's model. It looks a little complicated, but it's also simple. It's just that the interface looks old. That's why it's annoying to use, but it's also a simple system. Let me introduce you to some of the fields of it, and then before we get into it. Right, so starting in this region, this is where we are going to be putting our codes to be executed. So it will be receiving the assembly language. So the codes in the little man computer are taken in the form of mnemonics. Those three lettered instructions that are used to instruct the little man computer. Yeah, Joshua.
Please, I share your screen.
Yes, I am. Please, can you see my screen? Mr. Emmanuel, Auntie Mona, can you see my screen?
Yes, please, I can see your screen.
That's it. Yeah, don't worry. I'm using two devices, one for the audio, the other one for the video. I have reasons. So you'll not see it displaying on the Prince Wilson account, but you see it on the Prince Another Wilson. So, yeah. All right. As I was saying, the fields of the little man computer, this region right here is where we will put our instructions into the memory. The instructions that we put here are what will build the programs that the little man computer is going to run and execute on. Then we have this field right here where it says PC, program counter. So we know of the program counter to be the what do we call it? The register that holds the next instruction or the address for the next instruction to be executed. So this means if we are standing on an instruction on memory address 0, and the next instruction is to be executed at memory address 1, the program counter will always hold memory address 1, waiting for us to move to that. And once we move on to memory address 1, it updates to memory address 2. So it increments sequentially to keep or maintain the flow of the program. Right. So then we have the IR or the CIR, the current instruction register. What it does is it holds the instruction that is being executed in that instance. So depending on the model you are using, sometimes it will be holding number values for the instructions, but sometimes it will also be holding actual instructions like input or etc. etc. And there is the address register, also known as the memory address register or the MAR. The job of the memory address register is basically to hold the address of the current instruction being executed from memory. So whenever we are executing instructions or we are tapping from particular memory spaces, the memory address register is going to hold that very value so that the memory buffer register or the memory data register is able to tell which memory address it should visit to retrieve information to process on. Then we have the accumulator. The accumulator is a region of the central processing unit whose job is basically to perform arithmetic operations, more like store values on arithmetic operations. So whilst arithmetic operations are being handled by the central processing unit, it holds these values for these computations, the intermediate values as well as the final values, and even the start values that it will use in those computations are held in the accumulator. So if I am doing something like 2 plus 3, 2 will be held in the accumulator, and then it will be fed to the other regions of the ALU. It does the computation plus 3, and then the answer will be fed back to the accumulator. Mr. AK, please speak. Mr. A. Aquando, you may speak. Your hand was up. Okay, he clearly doesn't want to speak. All right, let's proceed. Yeah, so that's the accumulator for you. Putting that aside, we also have the arithmetic units, and then I guess you know what that is for arithmetic computations. And then we also have the input space. That's where we'll be entering input into the program, and output is where the results of our computations will be displayed on this side. The little man computer can only make use of very simple instructions. Let's look at a few of those instructions. But before that, study this region where it says RAM. We know that the RAM is the random access memory, and then what it does is it holds data values that are being executed on. Now, one thing that the little man computer does is it works on the von Neumann architecture, and then the von Neumann architecture uses the stored program concept where it stores data and then instructions in the same memory address. So what this means is the same spaces here that are used for coding data that we will be giving to the program will also be holding the very instructions that we'll be storing. So every instruction that you will put into the program will be held in a particular memory space. And this is why it's important that when you are giving data, sometimes you allot particular memory spaces to the data so that they do not get stored in regions where instructions have already been stored. Now, some of the instructions that are commonly used in the little man computer include simple ones. So we have data movement instructions, data transfer instructions like inputs. The P key on my keyboard has stopped working here, so I'm coming, relax. CQ's got fried recently. All right. So then the instructions that the little man computer commonly uses include INP for inputs. We know the output instruction, OUT. There is the load instruction, LDA. And then there is the store instruction, STA. So load address, store address. These ones are what we call data transfer instructions. So what they do is they basically move data from somewhere to another place, or they help transport data through the program. That's basically what they do. So they carry it from one memory address to another, or carry it from somewhere to their accumulator, or etc., etc. So these ones are called data transfer instructions. Then we have the arithmetic instructions. So in the little man computer, we have only two arithmetic instructions, and they are the add instruction and then the sub instruction. And then aside that, all these ones, the add and sub instructions, they always refer directly to the accumulator. So they do their operations in the accumulator, they affect accumulator values. Then we have control flow instructions, that's the branch instructions. Control flow instructions include the BRA, which tells the program to always branch. Then we have the BRZ, which tells the program to only branch when it encounters a 0. And then we have the BRP, which tells the program to branch when it encounters a positive number. Good. Then we also have the program control instructions, which are basically also flow, kind of like halts, written as HLT. The job of halt is to, and what do we call it? Stop the program or make the program terminate at a point so that it doesn't run endlessly. And aside that, we have data storage instructions that are written as that. So that most of these instructions, you will attach particular memory addresses to them so that you will guide them as to where they should display or put or store inputs. So for example, the load instruction, if you want to load an instruction for a particular memory address, so maybe I have a data in memory address 22 and I want to retrieve that data. So load carries that data and then moves it to another register. So if I say load the data in address 22, I'm basically telling the computer that go to address 22 and whatever you see there, read it. Then the next instruction is the store instruction. For the store instruction, you also have to attach a memory address. So if you say something like store 05, then you are telling the computer that it should go to the address 05 and store a particular instruction there. So it's storing in that address. So STA means storing the address. Then we have arithmetic instructions like add. Add basically takes data and then combines it with another. Now, if you want to use the add instruction, then it will mean you are moving data from one point, combining it with data in another point. So for example, I have loaded an instruction 22, right? After loading that instruction 22, then I may say add maybe what is in 22 to another instruction somewhere. So I have load 22 store 5. I may include another on top of the load. Perhaps I can say also, maybe I have another data value stored in address number 8. So I'll say load 22, load 8. Let me clear the store for now. And then I'll tell the little man computer that now load 22. Let me put the storage address here. Good. So store in address 5. Right. So then we had load 22, we stored it in address 5. So let's say 22 who held the data value, we loaded it and we stored it in address 5. After doing this, we also load the data value 8. And then now we are going to combine what is stored in 5 with that in 8. So now that we have loaded whatever is stored inside address number 8, it will be currently held in the memory buffer register. And now when we tell it to add that to memory address 5. Remember that we have stored the data value from memory address 22 in memory address 5, right? So if we say load 8, it will load the data value in 8 into the accumulator register. And then now when we say add 5, it's going to combine what is held in 8 with what is held in 5. And that value will be updated inside the accumulator. Then sub will be for subtraction. Branch always is an instruction that tells the computer that once you get to this point, jump immediately. So check no conditions. Once you get to this point, just jump. So for example, if I say branch 00, I am telling my program that whenever you get to this region, jump back to instruction 00. So whenever the program runs and it gets to this side, it will jump back to 00. It means you can use it to create loops in your program. Then we have the BRZ, which is branch 0. This means only branch when the result of a computation was 0, or only branch when you encounter a 0. So maybe I ask the user for an input. If I ask the user for an input and I put the branch 0 instruction here, so maybe I tell the computer branch 0 to address number 4 or 5. I'm basically telling the computer that if the person enters an input and then the input is a 0, jump to where address number 5 is. We'll come to that later. We'll use it in our coding, okay? And then there is also branch if positive. It does something similar. This time, if the result of a computation is positive, one input is positive, the computer will branch to a particular address that you will assign it to. And then we have the halt instruction that terminates the program, and we have the DAT instruction. Now, let's look at how the DAT instruction is a little different from the other ones. You notice that in all the other instructions, we put the storage or the memory addresses in front of them, so that we tell the computer where it's supposed to execute whatever it's supposed to do when it is dealing with this code. But for the data instructions, the memory addresses stay behind them. So for example, if I want to hold a particular data value in memory address 5, I will say 5 dots, and then I put the raw, the immediate value of the data that I want to hold. So then the data value is what stands in front of the dots. It is not a memory address. So if I put 9 here, 5.9 means in memory address 5, store data value 9. That's an immediate data value. It is not a memory address like the ones you see here. So now you will notice that all the instructions except the input and output instructions, they have memory addresses attached to them. So whenever you are calling these instructions, you have to attach memory addresses so that it knows where it should reference from. Every other instruction should have a memory address attached. Mr. Joshua, please help admit the people that will be in the lobby, okay? So that's basically a walkthrough of it. Now, let's say I want to write a simple instruction that receives the data from a user, stores the data, outputs the data, and then halts. Whenever you are doing these things inside a little man computer, the first thing you should always do is assign memory addresses to your instructions. Remember that we said in the von Neumann architecture, instructions as well as data, it's a limitation of it actually. The instructions as well as data are stored in the same addresses. So if you don't explicitly state where instructions should be held and where data should be held, you might end up overlapping the two. So you might be calling on a particular data or instruction value, but because that memory address was already used to hold some data or instruction value, you will be retrieving data that was never stored because the memory address that you're trying to store into was already holding a particular instruction. So we are always going to state the instruction what do we call it? Addresses. So for my first instruction, since I said I want a program that receives input from the user, stores the inputs, displays the inputs as an output, and then finally, the first instruction I'm going to store in memory address 0. That's it here. So execution in this computer program always start from 0. As you can see, it has already been highlighted. So memory address 0 is going to hold my first instruction, which is the input instruction. And then what is the input instruction? If you were following, the input instruction is what? Is it IN or it is INPUT, which is which?
IMP.
INP.
Must be all right. So INP for the input instruction like this. So now we have the input instruction. The next one is, I said we want to store it, right? So after we take the input from the user, let's store that input in a particular memory address. So let's say we store it in, first off, consider how long your code is going to be. Your instructions are going to be. I first said an input. We store the input. We load the inputs. We display the input, right? And then we halt. That means I'm going to need 5 lines of instructions. So it's advisable that you are going to use memory address 0, memory 1, memory 2, memory 3, memory 4 for these instructions. Therefore, if I decide to store my data value that will be inputted in memory address 0, 1, 2, 3, or 4, I am going to end up contradicting the code because it will already be storing an instruction on line 4 or in address 4. Therefore, if I decide to store my data value there, then there will be a conflict of storage. So it's important that you try to assign a higher register or a higher address to your data values, higher than the length of your instructions. Okay. So currently our instruction count is going to be 4. So let's finish writing it before we come and then assign the memory address to the storage. So I store the value, then I also load the value. After loading the value on line 3, I output the value. And then on line 4, I halt the program like this. So with all this said, then we can count. We have the instruction here, 000, and all the way to line 4. This means we'll be holding it in memory address 0, memory address 1, memory address 2, memory address 3, and then address 4. Therefore, it's not advisable to store your data inside any of the addresses, either 1 or 2 or 3 or 4, because your instructions are already going to be held over there. So you are advised not to store your instructions over there. So let's store it in a higher address like 10. That's a little far out of range, so I think we are safe when we do it there. So now that we've added the instructions, so I have stored it in 10. So if I am loading, I have to load from the same address where I stored, right? I load from 10, and then I output the value. For output needs no address. It will just display through the user's monitor, so the user's screen. And then input also takes input from your keyboard, so that will need no address. The computer finds ways of keeping that information on its own. And then the halt instruction also needs no address. We can use the DAT instruction to explicitly tell the computer that we are using memory address 10 to hold data. So no matter how long the instruction gets, do not store a data in memory address 10. We can do that by saying memory address 10 holds a data value. Since we are not storing a particular data value there, but we will be entering our desired data value, you initialize with a 0. Is that clear? So 10.0 just simply means that memory address 10 will be holding a data value that the user is going to update on their own later. So do not store any instruction there. So now we have 5 lines of code. So after doing this with the Higginson's simulator, you hit submit, and then those values that you entered here, they now become your instructions that will be executed. So now take a good look at this. You see all the instructions that we entered, and they have opcodes. The opcodes are a combination of the opcode and then the operand. The opcode is basically the code that represents these instructions you see. So for example, the input is represented by 9. Storage is represented by 3. Load is represented by 5. In the computer's language, out is represented by 9 as well. Halt is also represented by, oh, who is this? Ayensu. All right. Halt is represented by 0. So all these instructions here have their opcodes attached to them. Now, the operand is what we are doing our operations on. So the opcode tells the computer what to do. And then the operand will now tell the computer what it is using. So you are using address number 1. You are using address number 2, etc., etc. So then whenever you see your instructions, so now look at what we have entered here. It says if you go to address 00 here, we currently have 901, and it is holding the input instruction. What this basically means is that this here is a combination of the opcode and then something else. That has to do with the inputs that we'll be receiving, and that is being held in address 0. And this is why we cannot store any other data value in address 0, because it's already holding our inputs. Same applies to this 310 holding instruction here. So 3 for the opcode, which is storage, and then 10 for the memory address, which is the operand. So 310. So then the 3 tells it what to do, right? And then the 10 tells it what to use. And then we have 510. 5 for load, 10 for the memory address you're loading from. And then we have the output instruction 902. So the input instruction is 901, output instruction is 902. Halt is held as 000. And then the DAT values here currently, they are also 0, because we have said that we've initialized with a 0. If I should change the data value to anything else here, then the instruction, the address here is going to be updated with that value. All right. Now, let's run this program and then let's see what it gives us. So now there are 2 ways you can run your program. You can either run it entirely or you can run it in steps. If you run it entirely, what you're basically telling the program to do is it should go through all the codes and then execute them as needed. If you step it, on the other hand, it's going to be doing the execution one by one. So I prefer we do stepping first. And as we step, I want you to trace the increments that will happen in the program counter, trace what happens in the instruction register, what happens in the address register, and then the accumulator. Remember that the computer, the CPU, operates in three separate phases. It has the fetching phase, where it fetches instructions from memory. It has the decode phase, where it interprets the memory and the instruction into understandable forms by it. The execute phase. And then the execution is when it now does what the instruction required of it. So I'm going to step. Okay. So let's first reset and step. All right. So then upon stepping, let's follow what just happened. The program counter has incremented from 00 to 01. Remember that it holds the address of the next instruction to be executed. So it's telling the code that once you are done, follow on to instruction number 1. Now, on this side, the instruction register has now recorded an instruction, which is 9. And then the address register has recorded 01. If you look closely, you realize that it is the same as the 901 that was being held in memory address 0. So it means the instruction that was given, this is the instruction, the input instruction that is recorded as 9, right? And then it is held here. And then the address register says 01, implying that we are going to use 01 to execute our inputs when we are working. So then 901, keep that in mind. And then the accumulator stays 00 because the accumulator is used to hold data values, actual data values that are being worked on by the arithmetic logic unit. And since we have not done any computations, the accumulator now stays 0. Keep that in mind. And then, so this is the memory address register, it's holding address 01. So as we have done here, have you observed any changes to any of the RAM spaces here? So this will be questions that you will come across when you are working the questions in your assignment. So have you, aside the initial changes that were recorded in the registers, when we stepped it the first time, have you recorded any changes in any address? The answer is no. Because we have not moved any data value into any of the addresses, you have not yet recorded any changes. Let's step this again. So after we have the input instruction as run, it is now asking us for an input. So let's add the input. Let's use 8. So we hit 8 and we hit enter. Now it is carried out into the accumulator. So you see now the accumulator comes into play. It holds data values that are going to be computed later. So the accumulator is holding our input value 8. So now that we have done that, we can step it on to the next instruction. So when we step it again, so now, okay, it is being moved into the address for storage. So let's follow closely. After we stepped it the second time, program counter has now incremented to the next line. So it's telling the code that next time follow on to line 2 or address 2. After doing that, the instruction register is now holding the current instruction that we are executing. That is the instruction 3 here. And then it says that we are going to be holding that in address 10. Now, in more advanced systems, you'll be seeing the MDR or the MBR. Then what this register does is it holds the data. So the program counter tells the instruction register first off that we started on 00, so go to 00 and do something there. Instruction register holds the address, and then the memory buffer register will now go to that address and then retrieve the data from there, the data to be acted on. All this while the instruction register will also be holding the instruction in that address. So instruction register holds the instruction, memory buffer register holds the data, and the address register points to the addresses and then they follow its lead. Right. So now, if we trace carefully, you realize that there has been a change in one of the registers, particularly register number 10. It is now storing our data value 8. So the data value that we just entered is being stored in register number 10. Let's step the program again. And then you see there has been no change in the accumulator. Yo, what do you hear say why I mute why? All right, so then you realize the way it went and loaded the same data. So currently the last instruction ran the data and came to store it back in the accumulator if you were following the blue dots that was moving on the screen. So it means the load instruction has been executed now. So when you see those dots moving, the computer is basically doing the fetch, decode, and execute cycle. When it fetches the data, it visits a memory address. So when it visits a memory address, that's the fetching. The fetching means go and read whatever you see in the address. Now, when it reads that, it carries the data and then it brings it, it brings it to the instruction and the address register. There is the operating units or the control units. The job of the control unit inside the central processing unit is to decode the instructions that will be coming to it. So it will take the instructions and break them down into the operand and the opcode. It will hold the opcode in the instruction register and it will hold the operand in the address register. That way it can now interpret and see what it means. So the fetching is what happened first. And after the fetching, the data was now decoded. Oh, keyboard, why are you doing this to me? I'm coming on. My computer is doing some. It's Can you? I hope you can see what is happening right now. Yeah, I'm coming. And the words have taken over. Ish.
Brother, buy a new one.
Buy new laptop.
Yeah, I'll buy a new one. I don't have money. Relax. What is this? So hold on, okay? I'm coming. Hold on. I close this thing and open it too. Okay, let me just sign out. I'm not logging out. I'm just signing out on my device, on my computer. So my voice will still be active. You can hear me. All right. While I do that, I'll be asking some questions from you. Okay. Yeah. So I hope you can still hear me. Can you hear me? You can't hear me.
We can still hear you.
Nice. Yes. Times are hard. But we are harder. Okay. So my first question to you is this. Give me an example of an instruction in the Little Man computer that is considered as a data transfer instruction or data transfer instruction. An example of an instruction in the Little Man computer that is considered a data transfer instruction. Yes, who will take it? If you raise your hand, I won't see because on my phone I am not. I am just joining with audio, so my PC is coming back alive. Ish. Waiting with this.
Input.
Input, excellent. Input is a data transfer instruction. Who was that? Say it and let me clap for you. Whoever you are, I clap for you anyway, okay? Yes, aside input, what other data control, data transfer instructions are there? Instructions that manipulate data.
Load.
Load, thank you. Load address, LDA. That is also a data control, a data transfer. Yes. Any other?
Store.
Oh, excellent. Store is also a data transfer. Okay. What about a control transfer instruction? What about a control transfer instruction?
Halt.
Oh, excellent. Excellent. What else? Which other control transfer instructions are there?
That.
BRA.
DAT.
Branch instructions. Excellent. So they are also control transfer instructions. Branch instructions are examples of control transfer instructions. Yes. Nice. What else?
Hello, Prince.
Yes, sir.
Please, are you sharing your screen?
Hey, boss, you didn't get the memo. Yeah, my
Sorry.
computer was just doing some Kurakwedi right now, so I am working on that and then I'm sharing in about 10 seconds. Ish, that's come again. I think I changed it. I shouldn't have said 10 seconds. Okay. Uh-huh. Okay. We are back online. So is the other account still joined on the meeting? Okay, looks like it is out or it's still joined. Okay. I'm sorry for these small inconveniences, but understand I'm also a human being like you. Me too, I have mother son, so I face problems. All right, so we are back on. We are back on. We are back on. Okay, the power has been restored. The devil can try, but he's lying. Oh boy. Okay, so as I was saying, I've forgotten what I was saying. But as I was saying, the program counter will hold the next instruction to be executed. And then the instruction register does the decoding. So after we fetch, the decode will separate the opcode into the operand so that the computer understands it. Then after the decoding is done, the program now executes what the instruction wants. So during the execution phase, then we now start doing exactly what the program requires of us. Now, let's step this again. So currently we stepped it, we are on step 2. And program counter has reached 3. So let's step it. So then we expect the program counter to update to what? 4. And the way let me reset the program and do the stepping because it's not responding. Because I stop then start. Okay. So we entered input 8, right? And then we stepped it again. And we stepped it again. Let's step it one more time. So now the next step is for the output, right? The output is to display what we have. So it goes to it fetches the instruction 902, which represents output. It interprets it as output. Then the accumulator now feeds what it has to the output. So you see its data moved from the accumulator all the way to the output register. So it has displayed that for you. There we have it, 8. So you realize that this here means the computer has done fetch, decode, execute for every single instruction that it ran. And then the only time an address was changed is when we did the storage. So the address was changed when we stored a value in 10. So should there be a table and then there's a question that asks on step 1, what was the change or which memory address changed? What will you say? Will you say something changed or you will say none? Because actually none changed. And then if you step it again, if we were using this code, once we stepped on step 2, where the storage was done at address 10, address 10 was changed from 0 to 8. So then there is a change in address 10. When we stepped it once again, was there a change in any address? The answer is no. When we stepped it once again, was there a change in any address? The answer is no. When we stepped it again, no address changed. When we stepped it again, no address changed. Now, what were the changes in the accumulator as we stepped? When we inputted first time, there was no change in the accumulator. Or was there? When we did our inputs, was there a change in the accumulator or there was no change in the accumulator?
No change in
Wow.
accumulator.
Okay.
When we did
Mr.
our first
Joshua,
input, there was a change.
was there a change or there was no change? Mr. Joshua says there was no change.
There was a change.
There was a change. Someone
It
says
changed
there
from
was a
0
change.
to the input.
From 0 to 8, exactly. So since we entered the data value, so yes, Mr. Joshua, that's exactly what happened. Okay, it changed. Since we entered the data value, your accumulator changed. So if you were asked, was there any change? The input was initially not having any change with the accumulator, but afterward, so if there was a before and after phase for the inputs, before there was no change, so 0, but after it updated to your input, which was 8. Now, when we moved on to the store instruction, was there a change in the accumulator? No. When we moved on to the load instruction, was there a change in the accumulator? Technically, there was a load, and there was a change. Because if I step the program again, you're going to realize that when it gets to the load instruction, it actually goes to the memory address, retrieves the data, and brings it back. But because the same instruction that we stored at memory address 1 was the very same thing that we loaded into the accumulator again, that is why there was no change in the value. But you will realize that 8 was fetched again and then brought back to the accumulator. This means if I loaded an address that was holding a value like, let's say 20, then the accumulator value would have updated from 8 towards 20. So yes, there was a change in the accumulator during the loading phase. During the output phase, there was no change in the accumulator. During the hold phase, there was no change in the accumulator. That is all there is to it. Is that clear? So this is the basics of the central processing units No, the little man computer setup. This is how it runs. Do you have any good questions? Yes, Auntie Monica, ask away.
Please, you've not done the whole.
I've not done there. We've not halted yet. Oh, right. Thank you. So we step again. And it sends the address. It retrieves. It has read the address, taking the instruction, which is 0. So instruction and then memory address register update to 00. Right? And then this one is just to tell the program that there was a data value and then it was 0.
And
So
then
then the program,
DAT.
yes, that's DAT. So when we stepped this right now, the last step we did actually was the DAT. So we just halted and we stepped again for DAT. So for DAT, it just reminds the computer that that side holds a data value, blah, blah. So it has retrieved that information and brought it here. Now you realize that now the program counter holds an address that does not exist in your line of instructions here, right? So it's now on address 6. So each job is just to increment endlessly. Okay. However, we can loop the program counter by introducing a branch instruction. What a branch instruction is basically going to do is it will tell the program counter that when you get to this point, jump back to this particular region. So let's see if we can add a branch instruction. There are 3 different branch instructions. There is branch always, that's the BRA, branch if 0, that's the BRZ, and then the BRP, sorry, which is branch if positive. So in order to do that, let me reset my program. Let me step it. So the program has resetted. It's asking for input again. So let's stop running the program. And now we can edit our data here. Okay, so let's add the branch instruction right after output. So let's tell the program that when you get to this region, I want you to, or should we? Okay, yes, this side is fine. When you get to this region, that is instruction 4, I want you to always branch back to the inputs so that the program can run endlessly. So we'll tell the thing branch always to address 0. This tells the computer program that whenever you come to this line 4, the instruction here is telling you to jump back to address 0 and then repeat the sequence from there. These ones ignore the program counters sequence of operation. They break the flow and then they force the program counter to reset to the address that they desire. And after the branch instruction is executed, the program counter will now start incrementing from that very layer. Yes, Auntie Mona.
So when you use the branch, it doesn't halt, like it doesn't reach the halt instruction.
Exactly. So then normally the program counter would have followed on to the halt, right? But because the branch instruction has brought an override, so it has written what the program counter should do. So instead of the program counter going to address 5 to read the instruction there, it jumps with the branch instruction. So that's a jump instruction. It jumps back to the input. So in the central processing unit OS simulator, the actual instruction is the jump instruction. So you will see JMP. That is what does the branching. So yes, she is right to say that it doesn't halt. Since the branch instruction comes before the halt instruction, the program will not halt, but rather it will jump back to address that. Let me update the value here. So this is address 5, and then now we submit. So then input, store, load, output, branch, halt, data. But because of the branch instruction, we never get to halt. Let's see if this works. So step. Let me stop this. Fast. All right, let's reset it. I want us to just run it, okay? Because we know what will happen when we step. So when we run it, it comes to take our data So we input, let's use 78 this time. Enter. It's carried into the accumulator, blah, blah, blah. Then it's decoded. Now, what have you noticed? It has resetted. Or I think Stephen would have made it clearer for you. But now it has resetted again. And then now on the accumulator, the input is being required again. So I can enter a random input again, 78. Or let me use this time, 45. And I hit enter. It is loaded into the accumulator, and then the program does it again. It outputs it, and then it branches all the way back to 0, and it repeats the sequence. Okay, so the branch instruction is currently ignoring the sequential flow of the program, and then it is instead writing the program counter, forcing the program counter to reroute to a desired location. So it says reroute to instruction 00. Instruction 00 says input. So you give it inputs. So it gives 4. You hit enter. It does everything, runs through the program, it outputs it, and then it branches again back to 00. So that's how you use a branch instruction. Okay. Now, let's use the branch if 0 instruction, or branch if 0 instruction. Yes, the branch if 0 instruction. This one, how you can use it. The Little Man Computer is not a software that you use to do advanced programming and write programs for big projects. So please, it's just to understand how the program works. However, in a real programmer, or sorry, in a real compiler or in a real IDE code, in a real IDE, when you are writing codes, you can sometimes use particular phrases to cause conditions that will tell the program when to stop or start. We can use the branch if negative or branch if 0 instruction to do that. So maybe we are taking values from a user and we are going to stop exactly when the user enters 0. The branch if 0 instruction is going to tell the program that once the user enters 0, do this. So let's add a branch if 0 instruction, okay? So let's stop here. So I'm going to enter that right after input so that immediately the user enters an instruction. If the instruction is a 0, the program will stop automatically. But if it's not a 0, the program will overlook it. So that's the advantage of the branch if 0 instruction, right? So BRZ, and we update everything else accordingly. Okay, so 0, 1, 2, 3, 4, 5, 6. And so what we are basically telling the program is, if the user enters an input and it's a 0, let's stop. So how do we stop? Where is the halt instruction? The halt instruction is on line 6, right? It's in address 6. So we are going to tell the program that if the user enters a 0, jump straight to line 6 so that the program will halt successfully. So then that will mean branch to line 6, like so. So if the if the user enters a 0, branch to line 6, that's where the halt instruction is. So we load that into it and we have inputs. If it's a 0, branch to line 6, that means you will halt, because that's where address 6 means. That's what address 6 says. If not, store the data in address 10, load it out of address 10, output the data, branch back to inputs. So this means it is going to keep looping and taking input from the user until the user enters a 0. So it's a simple concept, like it's a very simple instruction, but see how it's working. So it's like the loops that you will be writing inside your coding environment when you are doing your actual coding. Let's use it and see. So we are going to be entering random values and then we will see what happens when we enter a 0. So we run. So it takes an input from me, I enter 4. We hit enter. It outputs it, so it loads, blah, blah, blah. I think our program is on acid right now. All right. Fast. Good. So then it has cycled through the program. It has outputted our 4. Let's enter another data, like maybe 98, and then let's step it again. Okay. Enter, blah, blah, fast, move faster. So it has stored at 98. Let's enter 7 one last time. It has stored that. Now, if I enter 0, let's see what happens. So once I enter 0, it says what? Program halted, reset, load, select or alter memory. So let's just focus on the program halted. So program halted means the program has stopped. This means once we entered 0, we fulfill the branch if 0 condition. So the program indeed branched to address number 6, and address number 6 holds the instruction halt. Therefore, it took the halt instruction and now brought it, decoded the instruction. That's why you see the 00 here. And after decoding that instruction, it's now executed it, and then the program successfully halted. So you are going to come by something like this too inside your assignment, and you will be asked the question that at what point did the sequence of the program counter break? And then you are going to have to mention that this happened at when the branch instruction was executed. So when the branch, if this happened, or branch always happened, that's when the sequence was broken. Is that clear? So there are other ones, the arithmetic computations, and then the subtract and etc. But I believe you know how to use them, right? So would you rather we move to the simulator and deal with it in the time that we have, or we just proceed with the LMC? In my opinion, let's go to the CPOS simulator because this LMC is a little more easier. All right, so CPOS simulator. And here we go. You can see my screen, right? Okay. I assume you can see my screen. Even if you can't see it, you can. Mr. Joshua, I beg, lobby the lobby for me, okay? Okay. Now, in the CPOS simulator, things are not as straightforward as they are inside the Littleman computer. The Littleman computer is like a far cry of the central processing unit, even though it is still supposed to simulate the operations of the central processing unit. It doesn't do it as detailed because it's trying to be as human-friendly as possible. The central processing unit operating system simulator, on the other hand, shows you in deep detail what these things are. The only difference that you will notice here is the absence of the accumulator. And the accumulator is absent for a good reason because it uses destination addresses to store data values. So then the job of the accumulator becomes a little obsolete. So it doesn't really include it. So pay close attention to this one. We'll run through it in the remaining 30 minutes we have. And then we'll better BBA say why. BBA be fine. I don't want to say you'll be fine so that you miss Nancy me. BBA be fine. Now, whenever you have your CPOS simulator, this region here will be holding the addresses that you'll be executing. This region here will be holding the name of the program and then the base address and then the start and then the blah, blah, blah. I have explained what the base address is before, but I am going to explain it again. You see these columns here, this one here where it says PAD and then LAD and then instruction and then the base and then the T. The PAD means physical address. The LAD means logical address. This is the instruction. This is the base address. And then T is the time taken to run a particular instruction, your clock rate, clock cycle, and all those things. Let's come back to this. The physical address is different from what we already know from the yeah. The physical address is different from what we know from our Littleman computer. And here's the reason. What it does is it starts execution from a particular place in the central processing unit so that no matter what you, the user, does, you won't have your programs interfering with the instructions, or you won't have your data interfering with the instructions. So the physical address starts execution at a particular line. That is always away from the earlier memory registers that will be there. What it does is it combines what we call a base address with the program counter value. And that becomes the physical address that the computer will actually use for the execution. Hear me out. It combines the base address with the program counter value, and then that is what tells the computer where it's going to have to start its execution from. We'll see that later. Then we have the logical address. The logical address is basically exactly how the program has been structured according to how much space each instruction takes. So the logical address is what the program counter uses for execution. So in our central processing unit operating system simulator, you can technically say that the addresses that you were seeing, they were logical addresses because they were also just exactly how the program counter executed its instructions. So the physical address is how it will actually be done, but then the program counter's flow, or how the program counter, the sequence in which the computer, the central processing unit will execute, based on the program counter is what the logical address is about. So physical address is the actual way the computer will work. The logical address is the sequence in which the program counter does the implementation. Now, whenever you are doing these things, you will have to add a few things to it. But before we go there, let's come to these sites and then let's explain all these fun, yummy registers you are seeing here. We start with the PC, and then we know that to be the program counter. We're already familiar with that. We know what it does. And then we have the SR. The SR is the status register. The status register basically talks about whether we have seen an overflow or whether we have seen a 0 or whether we have seen a negative value. And then it flags those things on this side with particular codes to tell you that we have seen this particular thing after running this particular codes. So the status register, it tells us what the results of our computations were like, where they look like, were they negative, were they 0, were they overflowing or what. And then we have the base register. And I've already mentioned the base register. The base register holds the base where we will start execution from. Then we have the instruction register, which holds the current instruction being executed. Then the memory address register, which was referred to as the address register inside our previous program. The job of the memory address register is to hold the current address that we are executing. So program counter holds the next address to be executed. Memory address holds the current address to be executed. Then we have the memory data register, also known as the memory buffer register. The job of the memory buffer or the memory data register is to hold or read instruction from memory or write instructions to memory. So if there is any instruction we are working on, the memory data register is the one that holds it, or is the one that will take that data to the memory and go and store it there. So know the difference between the memory address. It holds the address of the data. Memory data register holds the actual data in that address. So this is how program flows. Program counter first off tells the memory address register what address it is supposed to visit. The memory address register then tells the instruction register what it's supposed to do inside those things. So it takes the instruction there, and then the instruction register goes to the control unit, and the control unit decodes the instruction. After that, the instruction, if it has a data value to hold, it is carried on to the memory data register. The memory data register will also hold instructions as data during runtime. So sometimes you will see data and instructions inside the memory data register. There is one thing I didn't mention, that is the SP, and that is the stack pointer. Okay. I forgot what the P was standing for, but it has shown. So then the stack pointer, basically what the stack is currently all the addresses here, they are registers. Registers are very fast, what do we call it? Memory spaces that the CPU uses to process information. So it can quickly retrieve information from them quickly. So registers are like fast reminders. Yes, Auntie?
Please slow down, okay?
Okay. The time is moving, so I thought I would move fast, but I'll slow down. Slow motion is better than no motion. Okay, let's slow down. So the status, the stack pointer, I was saying, the job of the stack pointer is to force data into the RAM. The addresses that you see here are register addresses. A register address is different from your RAM. Registers are for storage. Your RAM is for storage, your ROM is for storage, and then your cache are also for storage. But they all play different roles. The fastest of them all is the cache register, or yes, cache memory, whatever you call it. Now, if we take these registers here, their job is basically to store data and then quickly move that data back to the central processing units. Some data values, they need to be accessed several times during runtime. For that reason, they have to be very close to the CPU so that they can cut the distance through which the CPU will travel to go and retrieve data and then come and operate on. And that's where the registers come in. So even though they are unable to hold data for long, they are able to remember data faster. So you can think of them as people that are having quick memory or quick retentive memory. And then program, this RAM also is able to store the data for longer than the register does. So all the instructions and things will be given, the execution and everything will be done based on the registers, unless we explicitly tell the program that push this program into or push this data into the RAM. It won't do that. We do the pushing into RAM with particular control or data transfer instructions that are called the push and then the pop. The push and pop instructions, I'm sure Professor Solomon from level 100, after or before he broke all our hearts and then gave us the 2 + 2 + 2 is 3, so monkeys can fly. No, before he did that, or after, he mentioned particular ways data is stored, and one of that was in stacks. And then he says there are two types of stack. There is the LIFO stack, that is last in, first out, and we have the FIFO stack, that's the first in, first out. This particular one here is an example of the last in, first out stack. So this means we can push data into it. Pushing data means you are adding data to it, and then when you push the data, the first data that you can take out will be the last data you put in. So think of it as a closed basket. What the entire share basket anymore? Now the move first. No, it goes to the bottom of the stack, right? The bottom of the stack is the highest point of the stack, basically. But in this program, the bottom is not the highest point. So at the end of the shame will last and first, no, it becomes the last clothes deep inside the basket. And as you keep piling up, the last cloth that you put in now becomes the first on the stack. So if you are going to take something from the basket, the first thing that you can take is the last thing you put in. That's why it is called the last in, first out. So LIFO, when you see that term anywhere, it's just referring to a type of stack register that allows you to remove the last data you put in first, last in, first out. So then that's what the stack pointer does. It's always pointing to the top of the stack. So currently it's pointing to the highest point of our stack. That's 8,096. Should we push any instruction into it, it is going to update to a lower value. All right. Let's move on. Let's forget all the idle talking and then let's start adding some programs to or instructions to this. So you can follow with your machines or you can just follow with your eyes if you are that visually fast. First off, you come to this section where it says program name, and you enter the name of the new program you're trying to create. So for this one, let's just use a random name. Okay, I don't know why I'm feeling Kasongo tonight, so let's use Kasongo. So then the program name is Kasongo. After we set the program name, we are going to set a base address. Remember what the base address does? It tells the program where it should start execution from. And it's important that you use this so that the program will not be mixing things up like in our other codes. And it also helps the computer to follow a proper sequence. So let's set a base address. Mostly I use 100, okay, because 100 is quite fine. So let's use 100. And after we do this, you come and here's the add instruction. The add instruction allows you to save or add this program to the, programs that are already existing inside your central processing unit operating system simulator. So now that I have added it, you see it is now in the program list, Kasongo, and then the base address is still at -1. Please untick this box, okay? And then once you untick it, update it with the base address that you entered, which was 100. Is that clear? And then if you want, you can save it. Saving it will mean you can later call on this program when you want to use it for something else. So let's save. So when you hit save, it is going to display your file explorer, and then it will show you a particular folder where all your programs are stored. So these are some programs that we've worked on in our earlier lesson. You remember we were doing demo 1 and etc. etc. So that's it there. So I'm going to store my Kasongo here, and there we go. So now that it is stored, it is ready to run. Okay, so now we have created the program. We now need to add instructions to the program so that we can execute those instructions and also feel good about ourselves and feel as if we are some high-tech programmers, even though we know we are not. So we go to this next tab here where it says instructions. When you go to instructions, it says add new. There is also show. Show allows you to see all the instructions that are present here. And then once you see the instructions, you can familiarize yourself with some of them. So I'm going to talk to you about a few of the instructions here, the ones that mirror some instructions in the Little Man computer, and the ones that are actual mnemonics that the Little Man computer doesn't provide because they are a little different and complicated to run in the LMC setup. So then the move instruction is used to copy data from a particular memory address. Okay, so that's a simple one. And then we have the load bytes instruction. Why am I skipping these ones? The answer is simple. I do not know what they are yet. Okay, I've not taken time to look at what those ones are, or I've never used them before, basically. So that's why I'm skipping them. And there is the load bytes instruction. What it does is it loads the bytes. Okay, so it loads an 8-bit instruction. And there is a load word instruction, LDW. And what it does is it loads a 16-bit instruction. That's the LDW. And then there is the LDBI, Mirifiano. But it also has to load bytes something. And then there is also load word something. And then there is also the storage instruction like store bytes, STB, or store word. Okay. And then going further, we have the push and then the pop that we mentioned that are used to add to the stack or remove from the stack. All these ones here are data transfer instructions. We use them to move data in and out. So if you are trying to add an instruction that's a data transfer instruction, you come to the tab up here where it says data transfer and you add. Okay. Now, there is also arithmetic instructions like your add, your subtract, your multiply, your divide, your increase, your decimals. I don't know if this is really in place. I've never used it before. And then the Subu or Subaru, I don't know. We'll look into that later, okay? But for today's lesson, they are just introductions. Yes, and I truly don't know what they are. Then there are the control transfer instructions. Control transfer instructions are the ones that tell the the program counter and then the program how to run. So jump. So you see the jump instruction I mentioned, the equivalent of the branch in the central processing unit. So this is the jump always instruction. And then there are loop instructions explicitly for looping. And then there is the jump if zero instruction here. If jump if not zero, sorry. So JNZ means jump if not zero. And then there is the JNE. I've forgotten what that is, honestly. And then there are other ones too. Let's see if we will see our jump. There is a halt instruction that we are so familiar with, so it didn't change form. There is a loop instruction. There is the JZR. Go and figure that out on your own and come and share with me the next time we meet, okay? So these are all control transfer instructions. And we have comparison instructions, okay? We'll come to that one very later, but then they are used to compare data. And then we have the input-output instructions. Unlike the central processing unit operating system, unlike the Little Man computer, the central processing unit operating system simulator doesn't allow for you to use input and output instructions to merely enter input and output. They rather point to input and output devices or input and output ports where you will be connecting your input and output devices. So if I add an input instruction with the IN, it is not going to run and then say I should enter an input. So we are not going to add any of those ones. We'll just be using the move instructions to be moving data into particular addresses and then combining the data and etc. etc. So let's just get right into it. So now we have seen what the instructions are. Let's add some of the instructions to this. Let's write a small program that takes data from a user, or no, that takes a data to a particular address and adds that data to another data in another address, okay? So it takes the data to a particular address. Then it takes another data value to a different address. Then it combines the values in the two addresses together. And then finally, the program halts. Let's do that. So since I want to move data, where do I start? Data transfer, right? So I use the move instruction. Whenever you select an instruction, you see these source operands that you see here. There is the value and then there is the register. If you are trying to enter an immediate value, right? And the PC is frozen again now. Why is this? Is it because the magnets are? Okay, sorry. Let's get back to it. Now, if you're a pointer moving, human beings, my pointer is frozen in place. Okay, it is back online. Good. If your aim is to move data and then you are moving an actual data value. So for example, if I am moving a data value like 6 or 5 or 7, that is an immediate data value. It is not a memory address. Then I am going to enter that inside the value column. So you are going to select value here. This time I want us to move a data value. Let's move a data value 30 into a particular memory address. Okay. So I am moving 30. So it says the source operand. It means our starting point. We are moving the value 30, and the destination operand is where we are going to hold the value we are moving. So I want to move the value 30 to register 11. So this means that if I add this instruction, when I run it, what it's going to do is it's going to take 30 and store it in register number 11. So I add that as a new instruction, and you can see the new instruction is added here. The physical address starts at our base address. The base address plus the program counter, which is 0 plus 100 over here. Now, you are going to see a difference in the way the program counter increments when we are running our codes. And then the reason is simple. The program counter increments not only in sequence, but it also increments according to the size of every data value it is storing. So for example, the move instruction, if it has a byte size or a bit size of 6, the next instruction is going to be at address 106. So the program counter is going to be increasing from 100 to 106 because the move instruction contains or is stored with 6 bits. So then it considers how many bits each data is stored or each instruction is stored, and it uses that to cause an increment in the program counter as well. So you will see that very soon. So we have moved 30 to register 11. Let's move another value. Let's move something like 10 to another register. Let's use another register. Which one should we use? Bluebird, how old are you? Let's use register 15. So then we are moving 10 to register 15. We move. So then, okay, good. So the move instruction is held in 6 bits of space. Therefore, the next instruction is on address 106. This means if the program counter is increasing, it will increase to from address 0 to address 6 instead of address 1. So it is still following a sequence. It will still tell the program how to flow, but it will do it based on the logical addresses, that's the program counter. Whereas the physical address will combine our base address, which is 100, with the program counter value, which is 6. So you can see them here. The first instruction was 100 plus the program counter 0, so then it was 0. Then 100 plus 6, which gives us 106. So now that we have moved our 30 to 15, our data values to the registers, let's add the 2 data values that are stored in the registers. So we go to the arithmetic so that we can add, right? So I am not adding immediate values, but rather I am adding registers. I'm combining what the registers are holding. So instead of saying add a value, I'll rather say add a register. So we are going to start with one register. Let's add register 11. It means that's our source operand. We are going to combine it with our second register 15 at the destination operand. And since register 15 is our destination operand, it means after the addition is done, when that computation is done, the value is now going to be stored in register 15 as well. So then let me add this as a new instruction. So it says you add register 11 to register 15. You realize the way we use hashtags to denote the immediate data values, and then we use R to denote the memory locations. All right. So what else can we do? We can add a push instruction that will force the data into the stack. But let's forget about that for now. And then we can also add our halt instruction so that the program does not run indefinitely. We can also decide to move the answer to a different memory address by using the move instruction again. But before we do that, let's just add a halt instruction. So halt is a control transfer instruction. So you go to control transfer, and then you go to the very last instruction, that is halt. And halt does not require a memory address whatsoever. We just add it as a new instruction. Good. So now that we have all these things stored inside our central processing unit operating system simulator, I should stop saying that, our CPU OS, let's just go ahead and then we step the program. So after doing this, let's first reset the program so that it resets to the first line here. So now that we have done that, what do we expect the program to do? It is first going to move 30 to register 11. So it means we should see a change in our register 11 here. When we run that line, it should change to 30. And then the second line is supposed to move 10 to our register 15. So we should see a change in our register 15. Third line is now supposed to combine what is stored in 11, which is 30, to what is stored in register 15 and store the answer still in register 15, since we said that's our destination operand. So then our register 15 at this line, after this line is stepped, our register 15 is now going to be incremented or updated from the 10 it used to hold to 40, which will be 30 plus 10 from the instruction that is given to it. And finally, we go to the halt instruction and then we stop. Okay. Let's not waste time. Let's go ahead and do this. So instead of running, let's step it. So if I step it once, the program counter increments from 0 to 6. The status register has not yet flagged anything. The base register is still at 100. There has been no overflow, no zeros noted, no negatives. The register 11 has now been updated towards 30. So then it means we have successfully moved data value 30 to register 11. So now let's step it again. We were here. Good. If we step it the second time, now we have moved to address 15, register 10. We have moved immediate value 10 to register 15. Now that we have done that, we can step again. And then what do we expect at this step? We combine 10 and then 11 and 15, and we store at 15. So you see, 15 has now updated to 40. That happened because it has combined what was held in register 10, register 11 to register 15, and then now it has stored that here to register 40. And then we can finally do the last step to halt the program. So once we halt it, it tells you the runtime of the central processing units. You see, it gives you in a very detailed manner. Yeah. And you will need these things for the clock rates and clock cycle calculations later. Not for this particular assignment though, but yes. So that's basically what the central processing unit operating system simulator is. If you want to add an instruction, so let's say I want to add an instruction that will now carry the data that was stored inside the address that was given. So if I want to move the data that was stored in this address, but I want to add the instruction under this without eliminating my halt, all I will do is come to insert below. So I'm standing on the third line. If I say insert below, I can give it a move instruction that will now move the data. So move instruction, that will now move the data that has been stored in the register. So I go to register. The data that has been stored in register 15, that's my source operand. I can move it to register, let's say register 20, and then I insert the instruction. After doing this, if I reset my program and then I run it again, you're going to notice, so let's do that. Step, 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 and then step again. Our register 20 is now updated with the value that was here. So it has copied the value and put it over here. So that's what the move instruction does. It copies data, moves it to another place. And when we halt this, the program will stop. I mentioned a time, 4 minutes to time. I mentioned, our time is almost up, but I mentioned the stack. Let's see how the stack works. We can add another instruction that the register data that has been stored here can be forced into the RAM, and then we can retrieve it later. So we can do this by pushing onto the stack. And that is the only time you will see a change in the stack pointer. Also, do you notice the irregularities in the increments of the logical addresses? So from 0 to 6, from 6 to 12, right? It means the first instruction, the move address, the move instruction was held with 6 bits. This one was also held with 6 bits. And then the add instruction was held with 5 bits. As you can see, it's incremented from 12 towards 17. And then the next instruction, this time, 22 on this side here. So it means there is a difference in how much bits that the data is stored. So this is why this is more real than the LMC, because it was just using increments of 1, which logically didn't make sense. If every address is holding data, then the registers will be spreading the data across addresses, basically. The RAMs, sorry. Okay. Now, let's add a push instruction so that we can force our data into the RAM, and then you will notice an increment in the stack. So the push instruction, we come to, let me add that below. So insert below, we look for the data transfer instruction, the PSH, and then we push the data that has been stored in register 20, or the one in register 15. Let's just use the one stored in register 20. We push that. So we are pushing it into the RAM, so we don't need a destination. If I insert that instruction and I now come and run this program again, so reset program, I step. Observe the stack, the program stack on this side. Step. It has now pushed the value to the top of the stack, 0022. And now the stack value has increased. So the stack pointer has now pointed to the new top of the stack, which is now 8098. So in the atadia bakwato so into stack na kosoro kakra. The TOS basically represent the top of the stack. So that's what you are seeing over here. If we do an arithmetic computation and we get a negative value or a 0 or something, we are going to see the flagging of the overflow or the 0 or the negative. Overflow is basically when you do a combination and then the answer you get is larger than the bits storage size. Okay, so if we're holding in a storage 5, a bit storage 5, and then the addition gives you a result that can be stored in 7 bits, then that will merit an overflow. So ladies and gentlemen, this is the end of my lesson today. I know there were some challenges, but I'd like to believe that at least the confusions you entered with, some of them have been cleared. In our next lesson, we will be covering what the assignment wants you to do. And I believe some of you said you don't know how to do screen recordings on your machines, which is, I don't want to sugarcoat. It's very, very shame. You should be ashamed of yourself. You should be ashamed of yourself for an IT student. But then we understand that we are distance students, so it's different for every single one of us. Some of us have not been exposed to technology all our life, so it's very understandable. Some of us don't even have computers. We code with books, and you can see what my computer does. So tomorrow I'll show you some software that you can use for recording, or you can use Microsoft's built-in recorder. But I believe the built-in recorder for Microsoft does not record with sound, right? So tomorrow I'll show you a little of that.
With sound.
It does record with
It
sound.
does.
So please, the bosses said it does record with sound. Okay, and then my machine has Bilibili because
Of course, it does record.
But your machine actually has Bilibili.
yeah, truly, I'll not lie to you. My machine has Bilibili. This machine, I am using this for a while. So yeah, you should respect it. It's older than you. Anyway, my machine has Bilibili, so it doesn't record with sound. So I use an external software that I downloaded from the Microsoft Store. So those of you whose machine have Bilibili like me, don't worry, we'll come to the club. We will just show you something else that we can use to compensate for the Bilibili the machine is having. So tomorrow we'll discuss the ins and outs of the assignments. I am sure the 2 hours will not be enough to discuss it. I will hate for us to carry it to another day because of late I've not been getting enough sleep. So I want to get time to sleep. But even if we can't cover it in one day, we'll carry it to the next. Just you make sure that
You can use the whole week for the assignment, Shami.
Oh, la, the guy. Oh, there you. Oh,
just make sure Semoba Mumbra na mumbi chiaska. Now I'm joining makeup class now, so that my workload will be reduced more. What's it?
Yeah, so no problem. Okay. Yeah.
Yeah. Some of you have paid, yes, I know. But some of you
yes,
know,
sir. Why can't you?
Ali, well, yeah,
Eh.
worldwide.
Yeah. When you want
All
to assignment, and then
Whoop free.
you.
right. Have a good night, everyone. We'll see you in the next video. Hopefully
Kudos
tomorrow.
to you. Wabi, kudos, Wabi. I must
Yeah.
admit, Wabi. Why are they?
Yeah, no glitch. Hopefully tomorrow it might be open to all as well. But even I want like that because Charlie, sleepless nights. So
Inshallah, brother. Do the Lord's work. I beg you. Do the Lord's work. If the money come, we will come pay. I beg you.
goodbye, everyone. See you in the next meeting. Have a nice night. Good night.